Hello, today we're going to go through paper 1, molecules and matter. So we'll start off with the topic of density. The equation for density is mass divided by volume, and it's important to know the units. So we've got kilograms, meters cubed, and therefore because it's kilograms divided by meters cubed, the units for density are kilograms per meter cubed. So when calculating density during a practical, you need to measure the mass using a balance, and to find the volume of a regular shape object, you can measure each dimension and then multiply them together. So the volume is just A times B times C. Or you can put some liquid inside a measuring cylinder, drop the object into it, and of course that will cause the liquid to rise. So as long as you knew where the liquid started and where it ended, you can find the difference, so you can then calculate the volume of your irregular shaped object. Just being sure that you avoid parallax errors, so you're taking readings at right angles. Or if you want to find the density of a liquid, firstly, get yourself an empty container, so here's a beaker, and then you put that on top of some scales and you find its mass. You can then add the volume of your liquid, and of course some different mass will appear on your scales. And then once you have done that, you then know the mass of your liquid, and you also know the volume. So then mass divided by volume will tell you its density. So it's important to also be aware of the different units involved with this topic too. So 1 kilogram, that's 1,000 grams, or 10 to the power of 3 grams. And 1 meter, that's the same as 100 centimeters, or 10 to the 3 millimeters. So that then means 1 meter cubed is 1,000,000 centimeters cubed, or 10 to the power of 6 centimeters cubed. And finally for this bit, that means 1,000 kilograms per meter cubed is equivalent to 1 gram per centimeter cubed. On to the next bit, which is states of matter. So you should be familiar with the idea of something being a solid, liquid, or a gas. And as you change between these, they are physical changes. In other words, they're reversible. You can go back. You can continually change between them. So we'll start off with a liquid turning to a solid. So that's, of course, freezing it. And if we go the other way, the solid is melting into a liquid. When a liquid turns to a gas, we call that vaporization. And when it turns back from a gas to a liquid, that's called condensation. Sometimes things can jump straight from a solid to a gas, and that's called sublimation. So if we were to look at what a solid might look like if we were to draw it, you'll notice that it's a regular shape. The circles are equally spaced and they're all touching each other. They're in a fixed position. They might be vibrating backwards and forwards, but they're vibrating about a fixed point. Liquids actually look quite similar to solids. The only difference is there are a few odd gaps. Each of the circles, each of the particles, they're all in contact with each other and they're able to move randomly around in the fluid. A gas, they're all separate from each other and they're very fast and they move randomly as they travel. On to the next bit, all about internal energy. So internal energy is made up of two parts, the kinetic energy and the potential energy. You add up the totals of each and that gives you the internal energy. So kinetic energy, or Ke, that's just the energy from the particles that are moving or vibrating. Potential energy, or Pe, that's the energy that's trapped between the bonds. Now when you heat up something, so in this case we've got some ice turning into some water vapour, a distinctive graph gets drawn. If we look at the start, where it's really cold and it's moving up to 0 degrees, the point at which it starts to melt, it's still ice at this point. So once it's warmed up to 0 degrees, it starts to melt. Now it's not an instant process, it does take some time to happen. Once it moves above 0 degrees, it turns to water and it starts to warm up again as it reaches 100 degrees, the point at which it starts to boil. And likewise, it doesn't boil instantly. It takes some time whilst at 100 degrees, and then it will reach a point when it will turn to water vapour. So to start with, we've got some solids. As it warms up, it turns into a liquid and then a gas. And as this graph suggests, the gas can indeed be hotter than 100 degrees. So the horizontal lines, the melting and the boiling, that's when the bonds are breaking. And that is all about our potential energy. And there's no change in temperature, known as latent heat. The kinetic energy parts, they're the ones with the gradient. That's when the particles are moving faster and faster and faster, and then eventually they move so fast that they can't move any faster, and that's when the energy is transferred into breaking the bonds instead. So let's look a little bit more at specific latent heat. So if we start with the equation, energy equals mass times specific latent heat. And the units, well, energy still measured in joules, mass kilograms, so the units for specific latent heat, joules per kilogram. The definition, so energy needed to change the state of 1 kilogram of a substance from Well, it depends on what you're changing to and from, whether it's going from solid to liquid or liquid to gas. So first of all, if we look at latent heat of vaporization, vaporization is when it goes from a liquid to a gas. So latent heat of vaporization is liquid to gas. So that means latent heat of fusion is going from liquid to solid. Now both can be the other way around, so it doesn't have to be liquid to solid, it could be solid to liquid, and vaporization could be liquid to gas or gas to liquid. So let's look at the practical involved for vaporization. So we have a power pack connected to an immersion heater, a heating element. That's then put in some water, and as the water heats up, some of the water will evaporate, it will vaporize. At the same time, it's in a nice bit of insulation to keep all the heat trapped in, and it's on some scales which of course will reduce in value as the water evaporates off. So just like with the specific heat capacity practical, in order to measure the energy, you need to know three things: the potential difference using a voltmeter, the current using an ammeter, and the time using a stopwatch. As well as having a low voltage, a sensible amount of time would be to have it on for 5 minutes, but as a reminder, you must convert this into seconds, and you must also remember to wear some eye protection. So once you've set it up and got your data, you need to calculate the mass of the water change to find the mass. So you know what the mass was at the start, and you know what the mass is at the end, so you need to find the change, and that can then be plugged into your equation. So you know the energy, you now know the mass, so the latent heat of vaporization, if we rearrange the equation, is LV equals energy divided by mass. So now let's look at the practical for the specific latent heat of fusion. Like previously, you need a power pack, and that's connected to an immersion heater. Inside our funnel, we have some ice that's starting to melt, and we've got a beaker down here that's collecting the water that came from the melted ice. And also, like before, the energy calculation is just the potential difference times the current times the time. You also want it on a low voltage, and for this one it takes slightly longer, so I recommend about 10 minutes, and again you'll need to convert that into seconds. What you need to use for the mass is the amount of melted ice that you have, and then you'll need to rearrange the equation for the latent heat of fusion, and like the other one, it's just energy divided by mass. Now let's move on to the final part, pressure and temperature. When you increase the temperature of a gas, it increases its pressure. Think of a lilo, put it in the sunshine, it immediately will start getting a little bit harder to sit on and a little bit firmer. So as it gets hotter, what happens is the particles increase their kinetic energy. What they're doing is they're hitting the container wall far more often with a much larger force. So if we plot a graph with pressure and temperature along the x and y axis, then the graph shape would look similar to this. So that just tells us that pressure and temperature are proportional to each other. So practical to do to measure this would be to put some dry air in a flask connected to a pressure gauge, and then you've got hot water that's being heated up using a heater. At the same time, that temperature is being measured using a thermometer. And also linked to this topic is looking at smoke, or also known as Brownian motion. Now the smoke particles we know are a lot bigger because we can see them with the naked eye, whereas there are also lots of air particles as well that are much smaller, but they're the things that are whizzing around really, really fast. So if you observe smoke through a microscope, what you start to see is the smoke moving in a zigzag, haphazard, random motion. And from looking through a microscope, what we can assume is that the larger smoke particles are being hit by lots and lots and lots of much smaller air particles that are moving really, really fast and colliding with the smoke quite often. And because there are so many that are colliding with it, there's enough force there to make it change direction. That now brings us to the end of the video. If you have any questions, please get back to me.